Okay, well, let's get started. Welcome everybody to the March 18th working group meeting. I'm pleased to see you all here. I'm pleased that we have two excellent speakers lined up for today. I remind you that the meeting is being live streamed and is recorded, and that the recordings will be available afterwards. So please take that into account. Our speakers have generously agreed to stay on half an hour after the meeting to have discussions with people who would like to discuss with them. That's purely voluntary, but it's a great opportunity to talk in a little more detail than the format that we have allows in the main meeting. So I hope many of you will take that opportunity. There'll be breakout rooms assigned, and you'll be able to join and speak to either or both of our speakers in more detail. So the usual reminder, Reinhardt can't be with us today. Co-lead with me on the working group. People will know Jim Sluka from his work on emails and also on scientific and website issues. And then everyone will know Bruce from the wonderful job he does organizing things. As always, I have to remind you there is a Slack channel. It only works if we use it. If people have other suggestions about better ways of communicating, that's fine. Also, please help us. The wiki page could probably use some love and some new material. So any group member can have access to posting on the wiki page. And if you need help getting access either to the Slack or the wiki, please contact Bruce or Jim. Please do take advantage of those facilities. I'll also remind you that tomorrow morning at 11 a.m. we have a steering committee meeting. The steering committee is generally composed of the people who are leading the various subgroups. However, if you think you should be on the steering committee and you're not, and you want to participate in yet another meeting, you are most welcome to contact us and let us know. We don't want to be exclusive on this. And if you are on the steering committee and you are going to be there and you have suggestions for agenda items for tomorrow, please let us know. The general rules of the meeting are, because the talks are very short, sort of teasers, the purpose of these talks, 15, 20 minutes max, is to give people ideas, to meet people, to understand things that are exciting, and to find new opportunities for collaboration and serendipitous connections. And because of the short format, the opportunity for questions, depending on how long people take, because it's hard for people to talk 15 minutes when they're asked to speak for 15 minutes. Some people do, but I know I have a trouble with that. We sometimes don't have as much time for questions as we'd like. And so if there is a question session within the meeting, we ask especially that we make room for those who don't always ask questions, because there's a lot of expertise in the room, and to focus on more general questions. Now that we have the breakout sessions, we have room for detailed and technical discussion afterwards. And if people seem to be running over time, I will give the speakers a 5-minute warning as a routine thing, just to remind people of the time limits. For upcoming meetings, as requested, we had a wonderful talk from Veronica last week summarizing the work done in the innate and adaptive immune response subgroup. Jacob Barak is going to give us a subgroup summary next week. And then we have David Otta talking at the University of Minnesota, biophysical modeling of viral life cycle, which I think will be quite exciting. Coming up, we have some very impressive speakers. Denise Kirschner will be talking about her wonderful multiscale modeling work on tuberculosis. And we have a couple of other very interesting people lined up a little further on who are going to be talking about various aspects of multiscale modeling and model sharing, and also on experimental work that they've been doing to validate these very, very complex models. I'd very much appreciate suggestions for future speakers. Anybody that you can find would like to hear, that's great. There also has been some suggestion that the working group meetings, the main working group meetings, might benefit from having occasional time to have more free-form discussion. April 1st, maybe that's ominous date, but April 1st, We have one speaker lined up. And so it's possible that we could use the other slot for a more free-form discussion. And so if there are people who have discussion topics that they'd like to raise to use this meeting for discussion purposes on April 1st, please let me, Reinhardt, and Bruce know, and we can use that slot for 25, 30-minute discussion of issues that might be of interest to the community. So I'd ask people for their ideas on that. If that works out well, we can move to having more of those. The alternative, of course, used for that would be to have one of the other subgroups present, if anyone would like to do that. So I also remind our speakers that if you don't get through all of the material you want to present in today, you're always welcome to come back and give a follow-on talk. Everyone who we've had speak has had so much material to present in the finite amount of time that they'd all be interesting to hear from a second time. So please feel free to say you'd like to come back. We hope we're a friendly audience for that. Okay, with that, I don't want to take up any more of our speakers' time. Our first speaker will be Yannis Kevrekidis from Johns Hopkins, who's worked on all sorts of very interesting mathematical issues related to modeling. And people who are regulars on this meeting know I don't do a big formal introduction. So I will simply turn it over to Yannis.
Thank you. So A, it's a pleasure to be here. B, do you see my screen?
Not yet.
Now we see it.
Yes.
Okay, very good. Okay. So okay, there is one basic thing I want to talk about. There's one basic idea, and then we can discuss it. The basic idea is the following, and this is why I think it maybe couples a little bit with the work that everybody is interested in here. When we do models in space, usually we do them in physical space. However, when you have problems in which agents are connected along networks and interact with each other along networks, they may live somewhere in physical space, but maybe physical space is not the space in which you want to write the partial differential equation. So if you work with networks, for example, and I will show you some example of this, then it's true that maybe the nodes of the networks are points in physical space, one neighborhood, one house, one person, but the neighborhoodness in physical space is not representative of the neighborhoodness of the behavior. And so what I'm going to try and talk about today is how to try and find nice spaces in which to embed complicated network dynamics so that they are effectively simple. Let's see how well I'm going to do that. But again, that's the point. The point is, if it's not a good idea to write a PDE in physical space, can we write a PDE in a smarter space, an emergent space, God help us to use the word, in which the system makes sense to be modeled as a PDE, in the sense that nearby behaviors are embedded near each other. Let me see how much sense I can make of this, and you will tell me if I did. First, something old. You know how the old professor says, oh, all of this is wrong, and I published it first anyway. So this is something from 1992, in which what we did is that we used neural networks at the time to learn partial differential equations. So if you have spatiotemporal data, but you don't know what the operator is, then how can you learn the operator online from data? The basic idea is very simple. Let me just say a simple thing. If you take so let's say you have a partial differential equation. If you have a few nearby points in space, then you can use finite differences to estimate the derivatives. And what is a partial differential equation? A parabolic one in this case. It is the time derivative at the mesh point as a function of the space derivatives at the mesh point. So when you have spatiotemporal data, every point in space-time from the solution that you have can be used to learn the PDE. And what you see on the right is, maybe it's not so clear, but the basic idea is by using a stencil of these 5 points, you learn the DDT in the middle. By learning the nearby 5 points, the DDT in the middle. So basically, this is something that by now is known. Convolutional neural networks are really finite difference stencils. If you don't have a sense of this, it's kind of fun to think. Okay, So this is something we've been doing for a long time, but the thing that we kind of started revisiting more recently is, what if you have a lot of fine scale behavior, agent-based, let's say individual-based, molecular-based, and you want to learn a partial differential equation for a macroscopic observable, for the density, for the pair correlation function. So you want to do hydrodynamic level equations from observations of agent-based things. And that is also something that is easily doable. You know, take my word for it, or you've done it. It's not difficult. You just look at the coarse-grained observations, and then you learn the PDE at the coarse-grained level. But what I really want to talk to you, this is a little example. So, you know, E. coli chemotaxis, for those of you that know Hans Othmer's work and many good people, okay, you can create individual-based models which at the macroscopic level close like Keller-Zegel or something like that. So what's the idea? You observe you run the microscopic model. If you know the right observables, let's say the cell density, what you can do is that you observe cell density as a function of time, and then you can go on and learn the chemotactic equations yourself. So this is a little example. Let me tell you what the movie is. What you're going to see on the left is 5,000 cells in one dimension. They are E. coli. They have internal states. They have 6 flagellae. Each one of them runs dynamically, blah, blah. And by the way, they're green, red, or green, yellow, or blue, depending on whether they go left, they go right, or they are tumbling. So this is a messy agent-based model. It is 5,000 coupled sets of two stochastic differential equations. You run it, and what I want you to see in the middle, the green is the chemoattractant, and then there is the blue and the red curves, where most of the time, what you do is that you just, they will just overlap visually. Let me run it. What you see is the agents running, and in the middle, the red is the observation of the fine scale model. The blue is the simulation of the effective learned PDE. So this is something to just say, this is easily doable. It's not a big deal. If you know what the right macro variable is, you run the micro, you learn the macro equation, and then you play with the macro equation. I am saying this to only say, let me say it once again, it's kind of not bad to see what all the agents are doing, and in the middle, what the PDF of the agents is doing, and also the learned effective chemotactic equation. Okay, on the right, what you see is how many cells at any given moment are tumbling, how many are going left, and how many are going right. So again, the main point in this, and again, I'm not saying anything, it's possible to look at micro and learn macro PDs. It's also interesting that if you know a part of the macro equation, so just only see where my pointer is at the bottom here, you can either learn as black box the entire chemotactic equation, or if you know a part of it, you can learn only the part that you don't know. So these are gray box PDE models. You can learn, let's say, only the closure for the chemotactic term. Okay, so in general, if you know the right quantity, let's say macroscopically, you want to look at the agent density, you can learn macroscopic PDs. What I want to talk to you about today is something that is more fun. So here is the fun part. Let me see if I can do a good job. I would like you to look at this map of Germany. On the right, there is cities in Germany on the map. On the left, what you do is that on any given day, you go to one of these cities, and every 5 minutes, you look if the sun is up. If the sun is not up, it's black. If the sun is up, it's yellow. So every city becomes a big Boolean vector of zeros and ones. But you understand, whether the sun is up or not is related to where they are on the map. If one takes these Boolean vectors and does principal components or something fancier like diffusion maps, then you find that this is a 2-parameter family of vectors. And if you project on the first 2 principal components or the first 2 diffusion map coordinates, or if you want on the first 2 isomap coordinates, you get something that is 1-to-1 with a map of Germany. I take this to be something like a realization of this English saying that handsome is as handsome does. Like you look at the activity and the activity tells you where you are, okay? So the idea is then that if you don't know where you are, but you look at what happens where you are, you can deduce where you are in space. So here is an example from a partial differential equation. This is a one-dimensional partial differential equation. It happens to be Ginzburg-Landau. This is space, this is time. The patterns are the solution of the PDE. What you do is that you take this data, this page as it comes out of your printer, and you put it through a shredder. You put it through a shredder and you get 512 time series, and then you scramble the time series. So now you have the activity at 500 points, but you don't know where the 500 points are in space. You will agree with me, I'm saying this very fast, but I hope I'm saying it okay. This is like having a puzzle. It's just that the pieces of the puzzle are long strips rather than being little squares. And by looking at which strip is close to which strip, so by doing data mining with smoothness as your main tool, you can solve the puzzle and you can reconstruct the space. So the idea is, I have space. I intentionally scramble it and just look at the behaviors without knowing where they come from. I can use the behavior, I can use data mining to put the behaviors together to reconstruct the space. So here is one version, one dimension in space. Here is a two-dimensional version. This is a 2D PDE in X and Y and time. What you do is that you take this cube of behavior and you push it through a meat grinder. You get 20,000 strings, okay? 20,000 time series. If you think of each of these time series as a data point and you do data mining, then you find that it was a two-parameter family of time series and you can reconstruct the space. Please notice it's not exactly the original space. It is something that is isomorphic to the original space. It's 1-to-1. So again, if there is space but you don't know it because you scrambled it yourself, you can look at the behavior and reconstruct it. You're going to tell me, thank you very much, you knew the behavior, you scrambled it yourself, and then you can say that you can unscramble it. Where is this useful? Here is where this is useful. Here is a whole bunch of oscillators. Each one of them is a little point. They are kind of going to be running around. This is one of the Strogat's interacting agent models, if you want. I run the oscillators. You look that they are colored with some funny color. Look, if I run them, then I find that they organize themselves along a very nice curve, which is parameterized by this color. And if I look at the behavior, the angle and the radius of the circle as a function of this color, then you find that it looks very much like a partial differential equation. So what I am telling you is, you look at the oscillators, and then you look at how heterogeneous their behaviors are, and by using the heterogeneity of the behavior, you can embed them in a very nice space. In retrospect, this space is the parametrization of their heterogeneity, in which the behavior looks like a PDE. So you can look at bunches of agents and then figure out in what space to embed them so that they look like a partial differential equation. And so what I'm going to do now, this is all the same idea that I was telling you. This is the last little example that I want to show. Here is 1,024 neurons. Each one of them is a set of, I think, 2, or it could be 16 ordinary differential equations. They are coupled in a crazy way. This is a Chung-Lu network. It's not all-to-all. It's not nearest neighbor. And what they do, as you see down here at the bottom, maybe, is that they synchronize. That is, each one of them is doing an oscillation. Of course, because they're all different, their oscillations are a little different. What do? You look at the oscillations, you do data mining on the behaviors, and then you find that, gee, this network could be embedded in a two-dimensional space. So these are two data-driven coordinates. They are emergent space variables, okay? Such that if you look at the behavior of the network in these variables, it looks like a discretization of a partial differential equation. So this is not a place in which I had physical space and I just rediscovered it. This is a place where there is no space, but by looking at the behavior, you realize that there exists a nice space in which you can embed the stuff so that nearby neurons in this space have nearby behavior, and you can model the thing as a partial differential equation. And my last slide is a movie of this. If you play the neurons, just naming them 1 to 1,000, you just get a mess. They are all kind of going up and down in a messy way. But if you look at them in this more intelligent space, hold a moment, let me play the movie again, which is on the right, then you realize that it really looks like a smooth behavior and you can learn a PDE. Why do I think this is maybe hopefully relevant for what everybody I perceive is interested, and my interest in this is that if you look at what happens to people, and physical space is a very bad variable to embed them and learn a PDE, then by looking at the behavior, we can discover what is the right deformation of physical space in which it would really make sense to describe the problem. So this is what I wanted to say. I hope I was, if not coherent, at least a little bit entertaining. The idea is, if you don't know what the right space is, data mining will tell you the space. I even think I have a summary slide. Let's see, here is the summary slide. Find the space in which you can embed the network dynamics first, and then learn the equation in that space. You can learn it either black box or gray box if you have an idea of what it would look like. That's it. I don't know how much more I ran than 15 minutes. I hope not much more.
No, that was perfect.
Okay.
Thank you very much.
So I can stop sharing.
So normally we hold the questions until the end, so that we make sure we get through both talks. I have to ask, since I guess I have the privilege, since I'm the MC,
the boss,
which is, I see how this works beautifully for deterministic systems.
yes.
If the behaviors are stochastic, do you have any way of doing something similar?
The quick answer is yes. You will then not have a partial differential equation on this, but you will be evolving a measure on this manifold. So
this would be more like your bacterial example, where the individual agents are stochastic. But
yeah, so there you saw an evolution. There you saw a PDE for the expected density. Okay, you can do not the expected density, but the expected density and its variance or something. So yes, it's doable. It is reasonable. It is not trivial, but yes, it's doable.
Well, thank you, and we'll definitely come back for more questions
Okay.
after the second talk.